In 9.1, we're going to learn how to graph a quadratic function in the form of ax squared plus c. So let's first review some vocab terms. A quadratic function is a nonlinear function that can be written in the standard form y equals ax squared plus bx plus c, where a does not equal to 0. And every quadratic function has a U-shaped graph called a parabola. The parent quadratic function is y equal to x squared. So this is when b equals to 0. So below is the graph of y equals x squared. And it goes through the origin, 0, 0. Okay, the lowest or the highest point on a parabola is called the vertex. So in this case, the vertex would be the lowest point. The vertex of the graph of y equals x squared is at the coordinate point 0, 0, which is also the origin. Now, the line that passes through the vertex and divided the parabola into two symmetric parts. So we're looking at this line right here. We call this the axis of symmetry. So basically, if we're looking at this point, it will be a reflection of this point about the y-axis. Okay, now we're going to look at how to graph a parabolic function, and then we're also going to compare it to the parent function y equals x squared. So we're going to look at some points here. When x is 0, y is 0. When x is 1, y is 7, and negative 1, 7, the reflecting point. And we can start graphing now. And this is 7 up here. Then we could connect these dots. Okay, now to compare the blue graph to the red graph, we can see that when the coefficient or the leading coefficient increases, there's going to be a vertical stretch compared to the parent graph. Okay? And then the domain and the range. The domain would just be all real numbers. And the range would be y greater than or equal to 0. Okay, and this one, there's something different. We have a plus 3 here. So when x is 0, y will be 3. When x is negative 1, then y will be 10, and the reflecting point, 1 and 10. Let's plot these points. Since this is 7, I'll add a couple more lines. So this is 10. So our new points will be here, and we can connect these dots. As you can see, the 7 remains the same, so the graph is stretched. So again, there's a vertical stretch. And let's be a little bit more detailed here. There's a vertical stretch by factor of 7. So you could write the same thing for the first one, this part, and then this plus 3 tells us that there's a vertical shift upwards along the y-axis. And the third thing we can say is that the domain is still all real numbers. And the range is y greater than or equal to 3, starting from this point. Okay, I could draw a dashed line. So this is the graph of y equals 3, and we want everything above 3 for the y values. And this one, and 0, 3, we got a vertical shift upward. And then now this is different. The parent graph, y equals x squared, has a leading coefficient of 1. Now this is a shrink. So if I let x equal to -1, I will get 3 1/7 as my y value, and then my reflecting point. And I can graph this one. You can see that the graph has become wider, or you can say there's a shrink. So we can say this is a vertical shrink by a factor of 1/7. And we also have a vertical shift upward by 3 units, and then domain, all real numbers, range, y greater than or equal to 3. Okay, to graph this one, okay, what's different now is we have a negative sign to consider, and still 7s to keep things simple. So if I substitute 0 in here, y will still be 0. If I substitute -1 in for x, this will be +1 times -7 makes -7. And the same would happen if I substitute 1. I'll still get a -7. So I could plot my points now and graph. As you can see that this parabola has been reflected in the x-axis because of this negative sign. So we can say that this negative sign means reflection in the x-axis, and this 7 means whether the graph is stretched or shrinked. Well, in this case, this graph is stretched, and then x squared is just the rest of the function. So in our description, in comparing it to y equals x squared, we can say this is a vertical stretch with a factor of, we can just write it short, factor 7, and it's also a reflection in the x-axis. And then there's no shifting, and our domain will still be all real numbers. We want all our x values. Range would be y less than or equal to 0. And if we look at this next example here, we have a -3. So this will tell us we're going to have a vertical shift downwards. This will tell us that we have a reflection, and this graph will be stretched by a factor of 7. So we can go ahead and graph these points here, -110, and 110's down here, and then we have 0, -3. And we can connect the points. Okay, so as you can see that this graph, there's a vertical stretch, by a factor of 7 compared to y equals x squared, and then it's also reflected in the x-axis because of the negative sign. And it's also shifted downwards by 3 units because of this -3 constant. And the domain, again, will touch on every single x-coordinate on the xy coordinate plane, so we just say all real numbers. And the range will begin here. We want everything less than or equal to -3. And now let's look at this case. This factor here has become smaller again, so it's going to be a vertical shrink, and this is a reflection, and this means it's shifted downwards. And after looking for all these points, let's see if the graph matches all these descriptions compared to the parent graph. So 0, -3, then -1, and -3 1/7, about here, and the reflecting point. As you can see, let's start with this negative sign. There's a reflection in the x-axis. And this 1/7 tells us that there's a vertical shrink by a factor of 1/7. Okay, and then x squared tells us it's a parabolic graph, and this -3 tells us that this graph is going to be shifted downwards, a vertical shift to be more specific, by 3 units. So from this parent graph, 1, 2, 3, shifted downwards. And then a little reflection. And our domain, it's still all real numbers, and our range, everything less than -3. So let's take a look at all these 6 graphs together. As you can see, when your leading coefficient becomes bigger, your graph will be stretched. And when you have a negative sign in front of that 7, the graph will be reflected about the x-axis. And now, when you attach a constant to the parabolic function, it will shift the graph up or down. And then in this case, this parabolic function is stretched and shifted upwards by 3 units, 1, 2, 3. And for this bottom graph here, this graph is shifted down by 3 units because of the -3, 1, 2, 3. And because of the negative sign, it's reflected in the x-axis, and it's also stretched by a factor of 7. So the graph is narrower. And this one here, the graph, the leading coefficient, 1/7, it's also positive, so there's no reflection. It has become smaller compared to the leading coefficient of the parent function, so the graph will become wider. So we call that a vertical shrink. Okay? And then if we add a +3 at the end of the parabolic function, it will shift the graph 3 units up, 1, 2, 3. And same thing for this one, -3, so shift downwards. Negative sign, reflection. 1/7, the graph becomes wider, or in other words, it's shrinked. So let's do a quick summary here. For the parabolic function y equals ax squared, compare with the parent function y equals x squared. The graph of y equals ax squared is a vertical stretch if a is greater than 1. So what I graphed earlier, this red parabolic graph here could be y equals 7x squared. And if a is between 0 and 1, meaning it's a fraction, this is going to be a vertical shrink. So this could possibly be y equals 1 over 7x squared, which I graphed earlier. And then for the next case, if you're comparing a graph of y equals ax squared with a that's less than -1, meaning your a here is negative. So earlier I graphed a y equals -7x squared. So we could let this be the red one here. We're going to have not only a vertical stretch, we're going to also have a reflection in the x-axis. And if we're graphing a parabolic function in which a is between -1 and 0, meaning this is going to be a fraction leading coefficient. So earlier I graphed a y equals -17x squared minus 3, but we'll just leave it as x squared here. Then we're going to have a vertical shrink with a reflection in the x-axis. So the 1/7 will make this graph, this fraction, will make this graph wider, or it will shrink it, and the negative sign will reflect it from the parent graph, and x squared, it tells us that it's a parabolic function. And lastly, comparing y equals x squared to the graph of y equals x squared plus c. So there's going to be an upward vertical translation, meaning it will slide up if c is greater than 0. So earlier I graphed a y equals 7x squared plus 3. So basically this plus 3 is a shift upward. And if you'll get a downward one if c is less than 0, or when it's negative. So it will be downward vertical translation if you have just the opposite, y equals 7x squared, let's say minus 3. This minus 3 will tell us we need to shift down. So this could possibly be the green graph, and your blue graph is your parent graph, y equals x squared. Okay, so all the blue graphs are your parent graphs, y equals x squared. Okay, let's practice. Tell how you can obtain the graph of G from the graph of F by using transformations. So this problem only wants you to describe in words, but I graph a picture for you so you can easily see it. So first of all, I graph f of x, which is the red graph. And then I graphed g of x for part A as well as g of x for part B, which is a different function. I should have used a different letter, but don't worry about it. So let's look at part A first. From the red graph to the blue graph at the top, we need to first look at by how many units did the graph move upwards or translate it upwards. So from -5 to the origin, there are 5 units. And from the origin to the vertex of 0, 8, there are 8 units. So that is a shift of 13 units upwards. So we can say translate. You first need to translate f, the function f, up by 13 units. And then we need to look at the coefficient of 2 and compare it to the coefficient of 1 here in f of x. So basically what happened was there's a stretch. You need to stretch the graph of G here, the one at the top, by a factor of 2. And that's all you need to do. And for part B, it's slightly more complicated. You also need to translate F, not up this time, I'm going to translate down. So from 5 to -8, how many units are there? There are 3 units. So we take the absolute value of that. So let's translate down 3 units. And then let's see. We have a fraction of -1/2, or just look at half alone and compare it to 1. Basically, there's a shrink. So we could say shrink the graph by a factor of half. And the negative sign, again, remember, it tells us that there is a reflection. So reflect the graph of f in the x-axis. And for this next problem, we are to write a function of the form y equals ax squared plus c, whose graph passes through the 2 given points given here. So hint, we're going to use linear systems. So first of all, I'm going to take 2 and 1, and I'm going to substitute it into the equation, the parabolic equation here. So that would be 1 equals a 2 squared plus c, so we get 4a plus c. And then I'm also going to do that for 5 and -20. So that's going to be -20 equal to 25a plus c. Now we're going to use systems to solve for a and c. So I'm going to eliminate the c. So a equals -1. And then I'm going to use 1 equals 4 -1 plus c. So c equals 5. Now we can take this y equals ax squared plus c and substitute in a. So a is -1, so -x squared plus 5, and that's our function. Okay, and let's take a look at this word problem from your textbook, number 43. The breaking strength, W in pounds, of a manila rope can be modeled by the function W equals 8,900 d squared, where d is the diameter in inches of the rope. So A, we are to graph the function. So this is in y equals 8,900 d squared. So you have a very big leading coefficient. So this leading coefficient is, this parabolic function is going to be stretched quite. And then, so because I don't have a lot of graphing space, so I'm going to make my increments very big. So this is the first thing I do. Plot the 0, 0. And then when it's -1, it's going to be 8,900. So that's going to be about here. And its reflecting point. Okay, and in part B, if a manila rope has 4 times the breaking strength of another manila rope. So I'm going to let rope 1 be W1, rope 2 be W2. So W2 will be our other rope. So this W2, I'm going to let it equal to 4 times the original rope. Okay? And then we want to know if this W2 will also have a diameter which is also 4 times. So let's do some variable manipulation. And remember, W1 is the original one, so we can say W1 equals 8,900 d squared. Apologize about this one. So we can substitute this in for W1 here. Now, I'm going to move the 8,900 out and move the 4 in with the d squared. And back to chapter 7, power properties, the product of a power So I can write 4 as 2 squared, and then I can rewrite this as 8900 2d squared. Now we can stop here and analyze this a little bit. Remember d stands for the diameter? Now the 2 tells us that when the breaking strength is 4 times the original one, the diameter will only be 2 times. So the answer will be no. Diameter is only doubled. Okay, and this concludes the lesson.